Here's a screencast to talk about silicon, and photovoltaic cells. The objectives of the screencast is to describe the doping of silicon to produce p-type and n-type semiconductors, and to describe how sunlight interacts with semiconductors. All right, so let's take a first look at silicon, located right here on the periodic table. You can see that it's a metalloid. So it has some properties of metals and some properties of nonmetals. That makes this a semiconductor. I'm going to write that. Ready? Semiconductor. That's written much nicer for you. Okay, and if we take a moment and look at ionization energies, and this is really the justification that you want to use in this particular unit, is the ionization energy and what that means. All right, definition of ionization energy is the energy required to remove an electron. Metals have lower ionization energies. Nonmetals have relatively higher ionization energies. Okay, so first ionization energy is the energy required to remove that first valence electron. Take a look at something like potassium, has 419 kilojoules per mole, all the way over here, bromine having 1140. Silicon is about 789 compared to like 1251 for chlorine and 496 for sodium. So that gives you an idea of the differences in the ionization energy. And those units were all in kilojoules per mole. Okay. So again, metals, good conductors. They have low ionization energy, so it requires very little energy to free up those valence electrons. They have fewer outer electrons. Nonmetals, poor conductors, also known as good insulators. They have high ionization energy, requires a lot of energy to remove that electron and let it flow for conductivity, and it has more outer electrons. Let's take a minute and look at this short video clip on metallic bonding, because it's important to kind of understand how metals bond to further this discussion.
Metal atoms have few electrons in their valence shell, and these are relatively weakly held. Though metal atoms group together in a crystalline lattice structure, they have very different properties to the ionic solids. For example, solid metals are able to conduct electricity. This is because the loosely held valence electrons of metal atoms are delocalized. They are not bound to one atom. Instead, they can move through the lattice in all directions. A sea of delocalized valence electrons surrounds the crystal lattice of the cations. The structure is held together by the strong electrostatic force between the sea of valence electrons and the metal cations. This is called metallic bonding. The electrons are constantly on the move, so the bonding acts in all directions. Metallic bonding is powerful enough to overcome the force of repulsion between the closely packed cations. The high melting points of most metals indicates the strength of the metallic bond.
Okay. Something to note that wait, I wanted to get to this picture.
Metal.
Oops.
But the ionic
When he talks about these being the metal cations, that is the inner core electrons and the nucleus. And because the valence electrons are free to roam, it does form a positive cation as that lattice structure, but it is the nucleus and the inner core electrons. Okay, so silicon and germanium are what are known as semiconductors. And a semiconductor is defined as a material that increases in conductivity with increasing temperature. The reason for this increase is because that increase in thermal energy allows more of the electrons to be released from the atom and move through that lattice. So because of the relatively low ionization energy, if I add more energy in the form of heat, that thermal energy, the semiconductors release more electrons and they can flow through the metal. It's interesting to note that metals typically decrease in conductivity with a decrease in temperature. Oh, increase with an increase in temperature. Increase in temperature. Okay, so metals typically decrease in conductivity when there's an increase in temperature. And the reason for this is that with that increase in temperature, you get an increase in the vibrations of the ions in the structure. So this causes an increase in the collisions. My computer is slow today. In the collisions between the ions and the electrons. And this actually causes more resistance to the flow of electrons. Semiconductors, I increase that thermal energy, I release more electrons into the structure. Metals, because their valence electrons are kind of already free to move, increased energy just increases some motion, causing more collisions and a resistance to the flow. So, silicon is a semiconductor. So the idea behind silicon being a semiconductor is when it absorbs heat, so electromagnetic radiation comes in, right, hits an electron, allows it to jump out of that covalent bond and travel. This causes a localized positive charge with a hole. Hold on while I answer my phone. So it creates, oh, what happened to my, sorry. So it creates these holes, okay, that other electrons are going to move into, and then create another hole where other electrons are going to move into. So you get the migration, really, of these holes and electrons, making them conductive. Okay. So, in those semiconductors, if we want to increase the amount of conductivity, they will typically do something known as doping. And in what this means is that you add a small amount of an impurity to increase the conductivity. Keep in mind that this doping is only done at parts per billion levels, so this is very dilute very low concentrations. The types of doping that is done, you either make an N-type semiconductor or you make a P-type semiconductor. The N-type, you actually dope this with arsenic or another group 5 element to make what is known as a negative carrier. That's what the N stands for, is negative, and we'll explain this in just a minute, okay? But it is a negative type semiconductor. It is doped really with a group 5 element, of which arsenic is an example. Keep in mind, group 5 elements have 5 valence electrons. P-type, if N is negative, P, hopefully you can figure out, is known as a positive type. Okay, and that is doped with a group 3 element. Element. That has 3 valence electrons. As an example, that would be gallium. So let's take a closer look at these. And again, just to show you, silicon, here is arsenic, gallium, okay, group 3, group 5. You do tend to choose a dopant dopants, that's an A. Dopant, that's the material that the silicon is being doped with, of a similar size to your nonmetal. That's a similar sized dopant to the semiconductor that you are doping. So, looking at an N-type produced by a group 5 element, we put arsenic in here with its 5 valence electrons. We end up kind of with an extra electron. And that increases the number of those free electrons. Okay. So that increase then allows for just movement of electrons through this structure, increasing the conductivity because I have that negative carrier to carry that negative charge throughout the doped silicon. Contrasted with the P-type, positive type semiconductor, it's doped with a group 3 element, such as gallium. Gallium only has 3 valence electrons, so this dopant introduces holes throughout the material, okay, and then you get electrons moving into the hole, leaving a hole behind, so you have that positive carrier. And the migration of holes throughout the system. In this case, the atoms or the dopant is called an acceptor. N-type, they're called donor atoms. And hopefully that makes sense because of the accepting electrons, or in the case of an N-type donor, that group 5, donating, calling it donor atom. Okay. If we flash back to this particular slide in these notes, I'm sorry. Just a little question. Do you remember hybrid? What is the hybridization of the silicon atom in this particular structure? Hopefully you remember it's sp3 because it has the 4 electron domains, tetrahedral in shape, right? Equally spaced, 109.5 degrees. Right? So under normal conditions, because of that covalent bonding, it's not a good conductor, okay? Semiconductor. Doping it makes it a better conductor. Okay. Sorry, just wanted to do a little flashback for you. Where were we? Ah, voltaic cells. Now we're up to voltaic cells. Woohoo. Oh. Voltaic cells are used to convert sunlight directly into electricity. They are constructed from both N and P-type semiconductors, kind of putting them together. Okay, and the big deal is that it converts sunlight directly into electricity. So what happens when we pair up an N-type semiconductor with a P-type semiconductor? This N-type, remember, it has excess negative charges, so it can move to the holes in the P-type semiconductor. Okay? So you get an overall flow of the electrons. Okay? Interesting thing here is that it allows for current flow. Sorry, hit a wrong button. For current flow in only one direction. Okay. And in order to keep this moving, we do have to connect it to a outside source. Okay, if we connect this outside battery in the wrong direction, meaning in the one that I have drawn, okay, plus side, minus side with electrons flowing this way, there would be no current allowed. Right? Makes sense, because electrons flowing here, it's not going to have any driving force to want to go into the N-type semiconductor. However, if I switch this around, make that the positive side, this the negative side, and connect it, electrons now would be flowing this way, and you would complete that circuit and allow current to flow. I'm hoping that made sense. I would draw two pictures if I were you. Okay, so now let's get down to the voltaic cell. How does this work? Well, I have my N-type connected to my P-type and my electrons flowing. As the electrons flow to go through this external circuit, spontaneously, electrons are supplied here to fill in the holes, electrons flowing here to fill in the holes, and we get a continual movement through here. What provides some of this flow and to create more positive holes is the sunlight releasing more electrons so that it can continue that flow. So electrons move from the N-type to the P-type, okay, depleting the N-type. That ends up with the N-type being positively charged and the P-type being negatively charged because of this migration through, causing a driving force to move the electrons this way and the holes to migrate that way. The sunlight providing the energy to free up those electrons. This process is going to continue as long as there is sunlight to create those holes in the movement of the electrons. Silicone by itself is a very shiny reflective surface, so a lot of times they will coat the silicon with an anti-reflective coat. So I hope you may have to replay this section a couple times to get all that down. Okay. So moving on, advantages of photovoltaic cells. 1, unlimited energy from the sun. We can harness all that energy. It reduces dependency on fossil fuels. There are no environmental issues associated with the use. Unlike nuclear, with the nuclear waste that has to be dealt with, fossil fuels with the burning, contributing to greenhouse gas emissions, acid rain, and the depletion due to mining. Another advantage is that there are no moving parts, so they are easy to maintain. No moving parts to get broken. Disadvantages of voltaic cells. They only operate when there's light out. The efficiency is rather low, 10 to 20%. You need a large surface area to generate enough energy to make it worthwhile. And the production of the cells themselves is expensive. Okay, and that's partly due to the preparation of the silicon. That ends the screencast on voltaic cells and silicon.